0, 1. And this section is on equilibrium and free body diagrams. So, okay, this is going to be a review because the prereqs cover this. Okay, so when you're given a machine element and you're given all the loadings and the way the machine element is supported, your first job is to draw a free body diagram. And the free body diagram gives you the forces at the support points. So it could be hinges, pins, rigid support, and so on. So here are some of the rules we need to use towards drawing free body diagrams. And we'll just be using these rules again and again. So first step is draw a free body diagram. Okay. And what it means to draw a free body diagram is you need to remove any support points and replace those support points with forces. Since it's a free body diagram, it should be free. It should be devoid of any things which connect that element with other elements or with the ground. Then we assign a coordinate frame. So this is the X and Y axis so that we can understand what reaction forces in the X and Y directions are. And the final step is we need to apply the equations of motion. Apply equations of static equilibrium. Okay, so in this course, we're not really focusing too much on things which are moving. We are only looking at things when they are stationary. So the equations are the summation of forces in the X direction is 0. The summation of forces in the Y direction is 0. And the moment is 0. So this is for planar bodies, right? Like I should just put that MZ. There's only for planar cases. If it's a three-dimensional object and you have three-dimensional forces, those forces, there'll be 3 forces in the X, Y, Z, and there'll be 3 moments, okay? And we'll restrict ourselves to 2D objects for this course, most of it. There's some cases where we'll do 3D, but you can think of 3D as, you can do it at 2 planes at a time, and then it's much simpler than doing a full 3D, and those things will come later in the course. Now, when it comes to reaction forces, there are a few things which you need to remember. Different types of supports induces different types of reaction forces. And I'm just going to give you a list of such support conditions. Okay, so machine element can be supported with a roller. That would look something like this. Let's say in this case is a beam, and it's supported by this roller, and that roller is on the ground. So this is just a part of it. So I'm showing the cut. And when you draw a free body diagram, you will draw this beam, okay, again, the cut, and you, in the free body diagram, you remove the support points, in this case, the roller, and you replace the effect of the roller with a reaction force. Now, since a roller is circular, it only transmits forces normal to the point which connects the body. In this case, it's going to transmit forces in the normal direction to the roller. So it's going to be a vertical force in this configuration. The next one, which is important, is called the pin joint or a bearing. Okay, and we're looking at 2D bearings. A bearing is shown in this course something like this. This is basically the bearing, the circular part. And let's assume there's a beam. And it's again cut. So we need to draw a free body diagram that would be just the beam without any support. And now we need to replace the effect of the bearing with forces. A bearing transmits 2 forces. There's a force in the vertical direction and the force in the horizontal direction. So move that around. Okay, so we'll call the vertical force as, let's say, V. It indicates vertical. But you could also use Fx, Fy, which is another way of writing it. So V for vertical, H for horizontal. Another way people draw this force is, instead of trying to draw as the two components, they draw a force like a reaction force, and they show an angle theta. Okay, so here clearly the force in the vertical direction is going to be the reaction force R times the component in the vertical direction. So R sine theta for the vertical force. Write that down. So V in this case would be R sine theta, and H would be R cosine theta. So both these methods are fine. You could use either of them, and they should give you the same answer. Okay, there's another support which is more in case of bridges, which is the fixed support. So in this case, we have a cantilever beam, and it's basically sort of like, almost like glued to the wall. So this, as I said, normally occurs in civil engineering applications. So in this case, what you would do is the free body diagram will look like this. The beam cut. The support I've shown you, the fixed support, leads to a vertical force, a horizontal force, and because it cannot quite, the slope at this point, at the connection point, is zero, it needs a moment so that the moment basically resists it from rotating at the support point. So there is an additional force M, any additional torque M. Okay, so with this, let's try to apply this and solve a simple problem. So again, this is going to be sort of a review. You've probably seen this in this before. Example. Okay, so a beam with a mass of 100 kgs is subject to a point load of 500 newtons. Okay, our goal is to draw a free body diagram. So I'll just abbreviate the free body diagram as FBD. Okay, so it's simply supported and it has a mass. So when you want to draw a free body diagram, as I said, what you want to do is isolate the beam from the support. So it'll just be without any supporting conditions. But because we've isolated it from the support, we need to replace the effect of the support with appropriate reaction forces. So for a beam, we would have a vertical force, a horizontal force, and then we would have a moment. So that takes care of the support. Now we also need to draw the right forces. So in this case, there's a 500 Newton force acting at 1 meters, but then this beam has a mass of 100 kgs. So there will be a self load due to the 100 kgs, and that would be acting, assuming that the mass is uniformly distributed, that force would be acting through its center of mass. The center of mass happens to be at the geometric center, which in this case, the middle of the beam. And that force would be due to the weight. So it's going to be 100, the weight, times G, which is 100 times 9.81, or 981 newtons. This is 1, and this is 3 meters. So this is the free body diagram, and that's all you need to do in order to draw that. Now, the next question could be, can you find the reaction forces, which you can using the equations of equilibrium. So that will focus on that in the next question. BD. Okay, so let's do another problem where we are.
Professor, I have a question.
Yeah.
So if there's not written like a beam has a mass of 100 kg, in this situation, it is written. So that's why we are putting like 981 force. If it's not written, then we don't include in our free body diagram.
Yes, that's right. So majority of the problems will not give you a mass, in which case you don't put any, you won't put anything there. Yeah, you'll put essentially W will be 0. So you don't have to show that.
Got it. Thank you, Professor.
Yeah. So normally these beams carry a load which is much, much greater than their actual weight. And that's why for most calculations, you can ignore the weight. In fact, for beams which are used in homes, so the reason why they can actually take more loads is because those loads are actually transmitted through the foundation to the ground. And that's why a beam which is of few kilograms can take loads which are a couple of tons because of that thing. In fact, if you are a mechanical engineer interested in rehabilitation robotics or assistive robotics, the whole point of having assistance, so think of exoskeletons which can make your legs swing faster and so on, are based on the idea that all the reaction forces, all the loads on the person are transmitted to the floor, and that way you don't have to carry additional weight. That's why people are able to lift big objects without straining their muscles. Okay, so next, let's do another problem, a slightly more involved one. Okay, so that's the figure. The problem is find the reaction forces at, we'll call this A, and we'll call this B. Okay, so we need to find the reaction forces at those 2 points. So what we'll do here is we'll follow the recipe I wrote down on the first page today. So draw a free body diagram, number one. Second is assign a coordinate frame. And third is use the equations of equilibrium. So those are 3 steps. So let's do that. First step is we'll draw a free body diagram. So we need to redraw this beam without any supports. Okay, so I removed the supports. Now let's put reaction forces. First, on the left side, we have a roller, and the roller transmits a vertical force only. So we'll put V for the vertical force, and we'll use a subscript A to denote the reaction force at A. At B, we have a bearing joint. So we would have 2 forces there. One is in the vertical direction, PB, and another one in the horizontal direction. And now you have an option of, well, in all these cases, you have an option of putting the arrow in the way you want. So in this case, I drew the arrow up for the, which makes sense in this case, but question is, would you put the horizontal force in this direction or that direction? So you can put either direction, doesn't really matter. What will happen is when you say you put it in, say I put it in the right direction, right? And I write HB. When I solve the problem, if HB is actually in the left direction, the sign of HB will be negative, and then I will just change the direction after I solve the problem. But you're free to assume any direction of your choice. Okay. So in my notes, I'll just follow my notes. I'll just keep it as this way so that it's consistent with my notes and I don't have to redo those calculations again. Okay, and then finally, we need to draw all the reaction forces. So we have the 100 Newton. And then 200. Okay, now we have a force which is at an angle of 45 degrees. In this case, the easier way to do this is, well, you could write it as 600 newtons at 45 degrees. That's one way. And then when you write the equations of equilibrium, you will basically resolve it in the way you want. But the other way to do it is to actually replace the effect of that force with a component in the X and Y direction, just make your life easy later on. So what I'm going to do is resolve this force right away in the free body diagram. So I'll draw that force in the vertical direction and in the horizontal direction. Okay, so this is going to be 600 cosine of 45, or sine 45 rather. So 600 sine of 45 is approximately equal to 424 newtons. And then it's the same force in the Y direction, X direction, right? Sine of cosine of 45, since sine and cosine have the same value, will be 424. Okay, so let me just start off cluttered. So I'm just going to erase this and just write the force. 424 newtons, 424 newtons. Okay, it looks much cleaner and it's much easier to work with. So the second step is to assign a coordinate frame, and you can draw that right on the, somewhere on the left or right, wherever you like to. So X, Y, and that's just to then use that meaningfully to write the equations in step 3. So when I write f of x equals 0, I'm actually looking at the x direction. So now let's write the forces in the x direction. We have HB, which is acting, as you can see, it's from the right to the left. So what I do is I put a negative sign because positive direction is to the right, as shown in my coordinate frame. And then HB, sorry, the 424 is acting in the positive x direction. This is the horizontal force, that is equal to 0. And from this, we can solve for HB. It's just 424 newtons. Okay, so next we can write the equilibrium in the y direction, which is the vertical direction. So you can see that the forces VA and VB are in the upward direction. So I'll put a positive sign with them. And then we have the 424 newtons acting vertically down. So I put a negative 424. And then there'll be a negative 200. And I believe there's another 100 newtons. So all that equals 0. So this will give me a single equation, which will be VA plus VB equals 424 minus plus 100 plus 200. That will be 724. Okay, so the last equation is the moment is equal to 0. Now, unlike the forces which are along the axis, the moment here is actually moment along the z-axis. Okay, so it's the z-axis sticks out. So it's really hard for me to show it otherwise, but it's basically the moment is something to do with the act of rotating something. So the forces are such that the beam doesn't quite rotate in the clockwise or the counterclockwise direction. So what we do is when we take moments, we need to take moments about a point. So we have a bunch of, well, we could take about moments about this point, that point, whatever you want. Just that if you take it about some of the reaction points where the reaction forces act, then you just save yourself some work. So that's why it's always recommended you normally take these moments about some points at which the reaction forces act. So point A is good because the moment due to VA will be 0 because VA passes through point A, or you can take it about B. So you can take either of them and you'll see that your answer is the same. So let's just take it about A. Let's write this as moment about A equals 0. Okay, so now let's just try to understand what these different forces are doing when it comes to moments. Okay, let's start with the easier ones. The 100 newtons is acting at a distance of, let's see. So just put this in the figure, 2 meters. 3 meters and then 2. Okay, let's go back. Now 100 newtons is acting downwards and the distance from A to 100 newtons is 5. So the moment is 5. The only thing left now is to figure out the direction in which this moment would act. So about A, you can see that the 100 Newton force will create a clockwise moment. Right? So it will create a clockwise moment, and our convention is typically that clockwise moments are negative, and so we'll put a negative sign. So that would be negative. Let's look at the 200 Newton force. So that's going to be again 200 acting. Well, let me put the magnitude first. 200 times the distance or the length of the beam, which is 2 plus 3 plus 2, that's 7. And as you see this, it acts in the clockwise direction. It's about point A, so negative sign. Okay, now we also need to find the moments due to VB and HB. So VB, as you can see, is upwards. So VB times 7, and the sign is going to be VB is upwards. It's going to create a counterclockwise moment. So we'll put a positive sign. Okay, now one thing which I should have made it clear is this is right in the middle. The way this thing is supported is it's a little bit weird, but never mind. So this point and this point are the same location. So HB doesn't really create a moment. The moment due to HB is 0. However, 424 Newton is actually not on the point, which is midway between the beam, and so it does produce a moment. So we'll come to that moment in a bit. So let's try the moment due to the upward force, which is the easier one, which is 424 times the distance from A to the application, which is 2 meters. And then since it's clockwise, we put a negative sign. The final one left is 424 in the horizontal direction. A is there. And so this 424 now is about point A. It's going to create a clockwise torque, right? Just look at A and see how the 424 Newton force rotates the beam or this line. okay, it rotates clockwise. So it has to be a clockwise torque. So put a negative sign, and the distance, I believe I gave it here, it's 0.2 meters. So all this should be equal to 0. So if you look at this equation, the last one I wrote, the only unknown is VB. Everything else is known. So we can pretty much solve for VB. Once we solve for VB, what we'll do is we'll put that in this equation. Let's call this 1. And once we know VB, we'll be able to solve for VA. So that's the way to do it.
Professor, I have a quick question.
Yeah.
So why HB is not included again?
Oh, HB acts. HB is acting exactly at the point where this point A is. It has the same horizontal vertical elevation as this point. If it was offset, then it would be. So this is perhaps a better way to show it. I showed it at round, but really it's something like this. And it's hard to show this because it's actually a 3D thing. So the way this is supported is something like this. Okay, and so the dotted part means it's not really here, it's inside. And so what happens is if this is so, then this line is the midline. And so the reaction force is acting on this. Again, the circle is sitting right there because that's how it's supported. I just drew it for purposes for illustration. So this HB acts here, and then since HB passes through point A, it won't produce a moment. That makes sense?
So it does make sense. So then why we included 424 times 0.2?
Sure. So this force here is sitting right here. Okay, it's on the top of the beam. But the beam itself is 0.2 meters half width, so it's 0.4 meters is the total width of the height of the beam. And so this distance is non-zero. That is 0.2. So in other words, so it's 424. This distance is 0.2. Just write it so that if you're referring it to it, then you can make sense.
Is there any way you could scroll down?
Sure, yeah.
So why do you have 424 times 2?
Yeah, so that comes from this force.
Oh, okay, yeah, I see. All right, cool, thank you.
Yeah, I should have maybe chosen a different angle, not 45. But yeah, so I think this will make it clear. Okay, so as I said, from equation 2, you solve for VB, and then in this case, you solve for VA. So put this VB in here, and you get VA. So I'm just going to copy what I have in terms of answers instead of solving it here. So VB comes out to be 405 newtons. This is from 2 on the previous page, and from 1 we can find VA. It is 724 minus 405 from 1. It comes out to be 319 newtons. Okay, so that's it. So that completes the problem. You've solved for the reaction forces.